We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Getting my feet up. Okay, I'm on.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 33 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 115 of the Space Rocket History Podcast. And now, Saturn I, SA-4, 5, 6, and 7. SA-4 was the fourth launch of a Saturn I launch vehicle and the last of the initial test phase that only tested the S-1 first stage. As with the first three launches, SA-1, 2, and 3, this would be a suborbital flight. SA-4 measured 180 feet in length, featured a maximum diameter of 21.4 feet, and weighed in at 1.1 million pounds at liftoff. The first stage propulsion system consisted of an octet of H-1 engines capable of generating a total thrust of 1.6 million pounds. Nominal burn time was 150 seconds. Just like the previous three launches, the primary goal of SA-4 was to validate the structural integrity of the Saturn I vehicle. However, a significant additional objective of SA-4 was to verify the guidance and control system's ability to properly handle an engine-out anomaly during the first stage of operation. Thus, one of the H-1 engines was programmed to initially shut down at approximately 100 seconds after launch. The test was to determine if the guidance and control system would respond properly to this anomaly by rerouting propellants to the remaining 7 engines and allow them to burn longer to compensate for the loss of thrust. There was a great deal of concern that shutting down one of the H-1 engines would create heat buildup caused by lack of coolant flowing through the engine nozzle. Some believed the engine would disintegrate, causing a catastrophic failure. Also on this flight, the dummy second stage was outfitted with aerodynamic design of the real second stage. This included vent ducts, fairings, and dummy camera pods. The rocket also flew with antenna designed for the Block 2 version of the rocket. SA-4 was also planned to test a retro rocket system that would be employed to aid separation of various rocket stages on later flights. After a very short checkout time of only 54 days, SA-4 went on to experience a very long series of holds during a countdown totaling 120 minutes. But on March 23, 1963, at 20:27 Universal Time, SA-4 was launched from Launch Complex 34 at the Cape. During the brief 15-minute flight, SA-4 reached a suborbital altitude of 129 kilometers and a peak velocity of 5,906 kilometers per hour. After 100 seconds of flight, a preset timer cut off engine number 5 as planned to test the engine-out capability of the booster. The guidance and control system performed correctly by rerouting propellants to the remaining 7 engines, which burned longer to compensate for the loss of thrust. As it turned out, the number 5 engine did not disintegrate from the loss of coolant as some had predicted. When SA-4 reached apogee, it successfully fired its retro rockets. Of course, on SA-4 the stages weren't designed to separate, so this test was just to make sure the retro rockets would fire. SA-4 was a very significant test, proving the engine-out feature of the clustered engine design. This survivability feature underscored the robustness of the clustered engine concept employed in the Saturn series of space boosters. As a matter of fact, the engine-out compensation capability demonstrated on SA-4 was successfully used during a pair of later Apollo missions, Apollo 6 and Apollo 13. All in all, a very successful 15-minute mission for SA-4. Now let's move on to SA-5. The Saturn I SA-5 had several major changes or upgrades from the SA-4. First, SA-5 was the first vehicle of the Saturn I Block II configuration. Second, for the first time, the Saturn I would fly with two live stages, the S1 first stage and the S4 second stage. The first stage was upgraded by enlarging the fuel tanks, so for the first time the rocket would carry its planned 750,000 pounds of propellant and would use 8 upgraded engines producing a thrust each of 188,000 pounds. The 4 outboard engines were gimbal mounted for directional control. The first stage also featured for the first time 8 fins, 4 large and 4 stubs. They were used to provide support and hold down points for the launch and, under certain conditions, aerodynamic stability during flight. The live second stage was powered by 6 liquid hydrogen, liquid oxygen Pratt & Whitney RL-10-A3 engines. All 6 engines were canted outboard 6 degrees and gimbal mounted. Interestingly, this engine design, RL-10, was meant to be tested several years earlier in the Centaur upper stage, but in the end, the first Centaur was launched only 2 months before SA-5. First and second stage separation between S1 and the S4 stages occurred between the S4 aft skirt and the S4 aft interstage. For the first time, the guidance and control computer on the rocket was positioned above the second stage. It was packaged with other instrumentation equipment, including the vehicle control system, tracking systems, and power supplies. The instrument unit's purpose was to control the ascent of the rocket through the atmosphere, automatically compensating for any winds or loss of thrust during the ascent. The S4 second stage was delivered to the Cape by a modified B-377 aircraft nicknamed the Pregnant Guppy. As with the earlier flights, SA-5 would still carry only a Jupiter C nose cone instead of a boilerplate Apollo spacecraft. The nose cone mounted to the instrument unit. Approximately 1,380 measurements throughout the vehicle were monitored during pre-launch and flight in order to obtain sufficient information to adequately evaluate the vehicle performance. The entire vehicle was 164 feet long and 21 feet at the largest diameter. It weighed 1.1 million pounds at liftoff. For the first time in the Apollo program, this flight would be an orbital mission. This was possible because of the upgraded first stage and the addition of the second stage. President John F. Kennedy referred specifically to this launch in a speech he gave at Brooks Air Force Base in San Antonio, Texas on November 21, 1963, the day before he was assassinated. He said, quote, "And in December, while I do not regard our mastery of space as anywhere near complete, While I recognize that there are still areas where we are behind, at least in one area, the size of the booster, this year I hope the U.S. will be ahead." End quote. The first scheduled launch attempt was for January 27, 1964, with all going well until 93% of the liquid oxygen had been moved into the first stage. At this point, the ground crew switched from fast fill to a replenish system. However, the liquid oxygen in the tanks began to fall because it was not being replenished. The cause was found to be a flange plate that was not removed from the liquid oxygen line. This could not be removed easily, and the launch had to be postponed for 2 days. Now I have a clip from NASA on the second stage testing and events leading up to the launch and the flight itself.
December 1963, Cape Kennedy, Florida. On Launch Pad 37B, preparations are underway for the first launch of a Saturn I vehicle employing a live second stage. This second stage, designated S-4, was designed and manufactured by the Douglas Aircraft Company. The primary objective of this mission is to flight test the Saturn I vehicle, which consists of an S-1 first stage and an S-4 second stage. For the S-4 stage, the major objectives are to achieve separation from the S-1 stage, to effect in-flight ignition of liquid hydrogen-fueled engines, to achieve engine operation until fuel depletion, and to place in the desired orbit the spent S-4 stage and the payload. The design of the S-4 stage and its operational systems, while based upon proven engineering concepts, required considerable pioneering. Several unique features are incorporated in the S-4 airframe, which must support the weight of its own 100,000 pounds of cryogenic propellants, plus the weight of the instrumentation unit and payload. April 1963, Santa Monica, California. The first S-4 flight stage, designated SA-5, completed manufacture and system checks and was ready for acceptance firing tests. Swathed in its protective nylon cover, in the quiet pre-dawn hours, the stage was transported to the Los Angeles harbor, where it began the 400-mile voyage to the Sacramento test site. May 21st, after final hardware fitting, SA-5 was installed in the test stand. The Saturn test stands had been provided with steam ejector blowdown systems to simulate engine operation in the vacuum of space. Because of an intensive testing program on the battleship tanks and with other test vehicles, loading of the cryogenic propellants was accomplished without incident. On the 12th of August, the full duration acceptance test was accomplished. During the test, all stage subsystems performed satisfactorily. The firing continued to a commanded cutoff. Residual fuel was less than 0.5%. All test objectives had been met, and NASA approved the test as a satisfactory acceptance firing. Following post-flight checkout, SA-5 was taken to nearby Mather Air Force Base and loaded aboard a modified transport aircraft. September 20th. The SA-5 stage was flown to the Atlantic Missile Range. The next day, the stage was unloaded and taken to the Special Assembly Building. For the next 19 days, SA-5 underwent a series of system tests and the final weight and balance checks. October 10th, Launch Pad 37B. The stage was hoisted into the stand and positioned atop the waiting S-1 booster. This photograph shows the 10 helium spheres which were carried on the flight to provide redundancy for the helium heater in the LOX tank pressurization system. The instrumentation unit was then positioned atop the S-4 forward interstage. This unit, weighing approximately 5,000 pounds, contained the Saturn vehicle's guidance and control package. The payload compartment was a modified Jupiter nose cone ballasted to weigh approximately 18,000 pounds. These three sections, The S-4 stage, the instrumentation unit, and the payload would not be separated, but would go into orbit as a single unit, weighing a total of 19.5 tons, 38,685 pounds. During the following weeks, the Saturn vehicle was given a comprehensive series of integrated checks. By late January 1964, all retrofitting had been accomplished on the booster stage, and the vehicle was ready for launch. Countdown was begun on January 28th. The count proceeded to launch, which was accomplished on January 29 at 11:25 a.m. Eastern Standard Time. Operation of the booster stage was nominal. First stage burning time was as planned. The S-4 engine chill-down operation, which was begun prior to separation, was successfully accomplished. At first stage engine burnout, the S-4 ullage rockets ignited. All enabling events were accomplished, and a successful separation was achieved. After separation, ignition of all 6 S-4 engines occurred as planned. Thrust levels were estimated to be nominal. Ignition and operation of the helium heater was satisfactory throughout the flight. The spent ullage rockets were jettisoned as planned. Step pressurization of the liquid hydrogen tank was accomplished. During the flight, operation of the S-4 telemetry system was satisfactory. Propellants were depleted as planned, and engine cutoff was accomplished as planned. Propellant utilization was estimated to be close to 100%. Operation of the flight control system was satisfactory throughout the flight, and at engine cutoff, the flight path was very close to nominal. The vehicle-payload combination went into an orbit having an apogee of 425 nautical miles and a perigee of 142 nautical miles. The primary objective of this flight test was to return experimental information on the flight performance of the Saturn I Block II vehicle. The knowledge gained from this flight will provide added reliability and increased performance in subsequent Saturn vehicles, vehicles which are already being prepared for future Saturn flights.
On the second launch attempt, SA-5 lifted off into overcast skies on January 29, 1964, at 11:25 Eastern Time. The rocket sent back 1,183 measurements to the ground during the flight, while at the same time it was tracked by 6 telescopes. For the first 1,000 meters, the rocket was filmed by 13 cameras that looked for any pitch, yaw, and roll movements. The separation of the 2 stages was filmed by 8 cameras that themselves separated from the rocket to be recovered 800 kilometers downrange in the Atlantic Ocean. The whole stage separation system worked perfectly, with the retro rockets firing on the first stage to decelerate it and ullage rockets on the S-4 firing to settle its fuel to the aft of the stage. After an 8-minute burn, the second stage entered into a 262-kilometer by 785-kilometer elliptical orbit. At 16,965 kilograms, it was the largest satellite ever to go into orbit at that time. However, the achievement of Earth orbit was not an objective of the mission, but merely a bonus. It did show to the American public that the United States had bridged the missile gap. The vehicle re-entered the atmosphere a couple of days later as its orbit decayed. Which brings us to Saturn SA-6. Saturn I SA-6, also known as AS-101, was the 6th flight of the Saturn I launch vehicle and the second of the Saturn I Block II launch vehicles. The first 5 launches of the Saturn I had carried Jupiter C nose cones, a proved design which allowed engineers to focus on development of the rocket. To verify the launch aerodynamics of the Apollo Command and Service Module, SA-6 carried a boilerplate spacecraft identified as BP-13. The boilerplate command module was an aluminum structure simulating the size, weight, shape, and center of gravity of a crewed Apollo module. It was a roughly 340 centimeter high conical structure with a base diameter of 391 centimeters and was covered with cork insulation to prevent overheating. The service module was a 391 centimeter diameter, 315 centimeter long aluminum structure mounted beneath the command module. Also included was a launch escape system with a live jettison motor. The 305 centimeter high escape tower was mounted on top to support a 464 centimeter dummy launch escape motor. The jettison of the launch escape system was set to occur after the ignition of the S-4 second stage. The boilerplate spacecraft was instrumented with 116 sensors reading strain, pressure, and acceleration. It had a mass of 7,700 kilograms, and the entire Apollo instrument unit second stage payload had a mass of 16,900 kilograms in orbit and was 24.4 meters long. SA-6 was the first orbital launch of an Apollo spacecraft by a Saturn Launch Vehicle, and also the first flight utilizing an active ST-124 stabilized platform. The ST-124 stabilized platform was part of the Navigation, Control, and Guidance System. Data from the ST-124 was used by the launch vehicle digital computer to compare actual flight data to programmed flight plans and to calculate guidance corrections. Though the ST-124 operated all during the mission, its data was not used for guidance while the vehicle was in the atmosphere, where it was subjected to high drag forces. In this region, basically the time of the first stage burn, the vehicle followed a simple pre-programmed flight plan. The flight plan was for the S-4 second stage instrumentation unit and Apollo spacecraft to be injected into a near-circular Earth orbit as a single body. The total weight in orbit would be approximately 38,000 pounds. Nominal orbital life of the payload was expected to be several orbits and then re-entry by random orbital decay with no planned recovery. The payload was to be continuously tracked by mini-track and radar to predict the time and area of re-entry. It took 3 attempts to launch SA-6 from Cape Canaveral's Air Force Station Space Launch Complex 37B. The first attempt was scrubbed after the liquid oxygen damaged a wire mesh screen during a test, causing fuel contamination. The second attempt was scrubbed after the rocket's guidance system overheated due to failure of an air conditioning compressor. On launch day, there were several delays during the count as liquid oxygen vapors obscured an optical window in the SA-6's instrument unit. This prevented a ground-based theodolite from seeing it. Now, a theodolite is an optical instrument consisting of a small-mounted telescope rotatable in horizontal and vertical planes. It's used to measure angles in surveying and sometimes in rocketry. This theodolite was required by the countdown computer in order for the launch to proceed. However, the engineers deemed it non-critical and reprogrammed the computer, allowing the launch to proceed. Here's the audio clip.
During the month of May, June, and July, the United States took large strides forward in space exploration. Under the direction of the National Aeronautics and Space Administration, the 6th of the Saturn I giant space boosters was launched on May 28th. All have been successful. 10 launches are scheduled for this phase of the research and development program. The next series, designated Saturn 1B, will employ a more powerful second stage and is slated as launch vehicle for the manned Apollo spacecraft. An active guidance system was employed for the first time on this launch of the Apollo boilerplate model. The payload, designed to eventually carry 3 men to the moon and weighing more than 37,000 pounds, was one of the largest ever orbited. Secondary objectives included testing of structural and flight control systems and jettisoning of the escape tower in flight. Standing more than 190 feet tall, the Saturn requires a service tower, or gantry, 37 stories high, thought to be the largest movable structure in the world. Saturn, mightiest of America's rockets, will develop over 1 million pounds of thrust to push it beyond Earth's atmosphere and into space. Consuming propellant at almost 6,000 pounds per second, the rocket roars into space. Special fiber optic lenses enable the onboard cameras to record propellant flow. The cameras are then jettisoned and recovered downrange by an Air Force pararescue team. Riding atop a tail of flame over 300 feet long, the space giant shoulders its way into the sky, sending to Earth vast quantities of information from the 1,300 sensing devices on board. Far above the Earth, cameras record separation. The spent first stage drops away and will burn up on re-entering the Earth's atmosphere.
The vehicle finally lifted off at 17:07 Universal Time on May 28, 1964. The ascent was normal up to 117 seconds after liftoff. At that point, engine number 8 shut off early. This was not part of the flight plan as it had been on SA-4. But SA-6 compensated perfectly by burning the remaining fuel in the other 7 engines for 2.7 seconds longer than planned. The first stage separated and the second stage ignited. 10 seconds later, the launch escape system was jettisoned as planned. Also jettisoned from the first stage were 8 film cameras that observed separation of the stages. The second stage cutoff was at 625 seconds after launch, with the stage and the boilerplate craft in a 182 kilometer by 227 kilometer orbit. The final orbital parameters for the upper stage and attached Apollo spacecraft were very close to those predicted. The spacecraft's spin rate of 28 degrees per second was faster than desired. It was caused by venting of propellant residuals. All spacecraft systems operated as planned during countdown and flight. Telemetry was obtained from 106 measurements until end of battery life on the 4th orbit. Vehicle made a total of 54 orbits, re-entering the atmosphere east of Canton Island in the Pacific on June 1st. No spacecraft recovery was planned. Now for the engine failure. Engineers were quick to find the cause of the failure of engine number 8. The teeth on one of the gears in the turbo pump were stripped off. Fortunately, this did not cause any delays in the next launches, as the engineers had already decided that the gear design was inferior and were planning to change it for the next launch. This was the only problem encountered with an H-1 engine during flight. The SA-6 launch proved that Marshall could build a booster to fit the command module. In the jargon of the trade, the mission was nominal. Which brings us to SA-7. Just 3.5 months later, on September 18th, a nearly identical test of the 7th Saturn I took place. SA-7, also known as AS-102, was the 7th flight of the Saturn I launch vehicle. SA-7 was designed to repeat the flight of SA-6. It would once again carry a boilerplate of the Apollo Command and Service Modules, BP-15. The biggest difference between boilerplate 13 carried on SA-6 was that on boilerplate 15, one of the simulated reaction control system's attitude control thrusters was instrumented to record launch temperatures and vibrations. Another major difference on SA-7 was that the launch escape system tower would be jettisoned using the launch escape and pitch control motors. Physical dimensions and weights were almost identical to SA-6. In early July 1964, a small crack in the engine number 6 was found. This meant removing the engine, the first time that the ground crew had to do this with a Saturn rocket. It was then decided to return all 8 engines to the manufacturer, which meant a job that took about 10 hours because the large number of tubes, hoses, and wires that connected each engine to the rocket. The replacement delayed the launch by about 2 weeks, followed by another delay of several days because of Hurricanes Cleo and Dora. A little before noon Eastern Time on September 18, 1964, SA-7 was successfully launched from the Cape. The first stage burned for 148 seconds, with separation 0.8 of a second later. The second stage ignited 1.7 seconds later, and the launch escape system jettisoned at 160 seconds after launch. It burned until T plus 621 seconds. The Saturn I placed the boilerplate Apollo Command and Service Modules, the instrument unit, and the spent S-4 stage in an Earth orbit similar to the interim orbit planned for future Apollo missions. An elaborate system of 8 motion picture cameras and 1 TV camera was mounted on the S-1 stage to record flight events. The motion picture cameras were ejected following the S-1 powered flight, but were not immediately recovered. The failure to immediately recover the 8 film camera pods was the only anomalous event of the flight. The cameras had landed downrange of the expected area where Hurricane Gladys ruled out a continued search. However, 2 of the pods did wash ashore 2 months later. The pods were covered with barnacles, but the film inside was undamaged. Telemetry was obtained from 131 separate continuous measurements. All test objectives were met, including final verification of the Saturn I propulsion, guidance, and structural systems, development testing of the Apollo spacecraft during atmospheric exit, test jettisoning of the launch escape system, and compatibility of the command and service modules with the launch system. The spacecraft orbit decayed to the point of re-entry on September 22nd after 59 orbits. The end of a very successful flight for Saturn SA-7. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.